Hey, Trip0 here, and I prepared some cool information about CO2 and how it can be used not only for plant usage, but to understand different elements of what's going on inside your greenhouse. So this is primarily for greenhouses, but can be applied to any sort of indoor growing situation as well. So let's move on, start the presentation. So this works, I'm going to talk about this as part of a system. It doesn't necessarily apply completely to the system. It can obviously be used outside this type of system, but I'm going to talk about this as part of a bigger geothermal water system. And what a geothermal water system is a greenhouse that has some geothermal mass, some soil that's used to either heat or cool water, which in turn is used to transfer energy around different components in the system to try and maximize the efficiency of the system as a whole, move the energy where we need them or away from things that don't need the energy to heat, cool, things like that. So in this part, we'll be talking about the CO2 generation system, which has the CO2 cloud right above it. And perhaps in future videos, we'll talk about the other parts of the system and how they all work together. So first off, plants need CO2. They use CO2 and water plus some solar energy, and they create glucose, and they release oxygen into the atmosphere. So this is an interesting process, but CO2 and water are the main parts of this process, along with solar energy, of course. This is a graph from my greenhouse. This is the data I've collected. And in the green lines shows the light levels. So during the day, it fluctuates quite a bit, but at nighttime, the area highlighted in yellow, light levels drop to very, very low. Meanwhile, in blue, we can see the CO2 levels measured in parts per million, and it's inversely correlated. So when the light levels go up, we can see the CO2 levels will go down. And that's because the plants are conducting photosynthesis. They're consuming the CO2 and they're producing sugars. So that's really cool. It's probably most pronounced over here at the 9 o'clock and beyond section, where the CO2, as soon as the daylight starts coming in and the light starts going up, the CO2 level drops off quite a bit. And during the nighttime, the CO2 levels go up as high as they can. They'll basically match atmospheric levels during the day or during the nighttime, and during the day they somewhat drop below. Now, don't be thrown off too much by the parts per million. My sensor's out of calibration. Atmospheric CO2 levels are around 400 parts per million. So this is a little bit higher, but you get the idea that, during the daytime, closed environment like a greenhouse or inside a grow room, you have these types of fluctuations in the nighttime and the daytime, and when there's light and not light. So if it's consuming more CO2, that should mean that there's more growth. So doing some calculations, I came up with the ratio of 10 to 6. 10 grams of CO2 will produce about 6 grams of glucose. And that's not just CO2. Of course, there's water involved, and some oxygen is taken away from there. But if you want to go into like how that math works out, this is how it works out. CO2 is about 43% carbon. The oxygen you can basically just throw away. It's released into the atmosphere, and then it uses all of the water molecule, adds the carbon to it, creates the glucose, and the whole glucose structure is about 40% carbon. So, methods of generating CO2. 3 main methods. There's probably a lot more. There's compost. Some people build compost piles in their greenhouse that will generate CO2. It has to be aerobic type decomposition, aerobic type bacteria that oxidizes the glucose and the other carbon-based structures inside the compost material, and then creates CO2 from that. If you don't have oxygen, it has to be well oxygenated. If you don't have it well oxygenated, then it can create anaerobic reactions and create something like methane, which you may not want inside your greenhouse. You can also get CO2 from bottles. This is typically more expensive, and the least expensive and the most productive way is to take a hydrocarbon, which could be methane, which is CH4, or natural gas is mostly methane, but has other things in it, including propane, liquid petroleum gas, and other types of hydrocarbons. You basically burn those. It oxidizes the hydrocarbon. It creates, as a byproduct, CO2 and water vapor, typically, when you burn it. So this is what I have inside my greenhouse, and it meets the it fits well in this system. So it's water cooled. I can use the existing water system to cycle water through it. This has the effect of cooling it. If I were to use this in, for example, I did use this for brief periods during the summer when the morning temperatures were cool enough before it got too hot. So I would crank it on in the morning, and I can keep it going longer, produce more CO2 if I can keep it cooler. So the water cooling definitely helps in that regard. I think it removes up to 80% of the heat, and then the rest of the heat is exhausted out the top. And then it also doubles as a water heater in the wintertime, which is also excellent. So during the day, I can burn CO2. I can transfer that heat into the water, which then transfers the energy into the geothermal mass, or my water reservoir, which is somewhat large. And those things are going to keep the energy until nighttime when I really need it. So I'm basically creating CO2 during the day when the plants can use it, and then saving the heat that it's generating for the nighttime when the plants need it as well to stay warm. And then it makes plant food, so it has excellent utility. There are other CO2 generators. They're basically burners that don't have the coils inside it like this one has, but it achieves the same purpose, at least as providing heat and plant food. You can, of course, during the day, you got to be careful with the heat because greenhouses tend to get hot when there's sunlight coming in. So what are the ideal CO2 levels? It may depend on the plant. Some plants use CO2 more efficiently than others. There are 3 types of plants that use carbon in different ways. There's the C3 plants that rice, wheat are some examples. There are C4 plants like corn that use CO2 a little bit less efficiently, I believe, or perhaps I'm not. I may be going off into the weeds here, but anyway, if it's a C3 or C4 plant, it's going to benefit from some higher level of CO2 than in the atmosphere, but to a limit. After about 1,500 or 2,000, depending on the plant, it can no longer use any more CO2. It no longer does any more photosynthesis. Basically becomes saturated, maxes out, in other words. If it's a CAM plant, CAM, that's the 3rd type. Those actually consume CO2 in the nighttime and then store it as acids and then utilize it during the day. So those are typically not plants you grow in for food. Those are like cacti and other desert plants that to be breathing in warm CO2 during the day, it's overheat the plant and things like that. So they do the breathing at night, store up the CO2, and then breathe it out during the day to keep cool. I measure CO2 2 different ways. The sensor on the left is the Sensor S8. I have the residential version. The commercial version is probably better, and I wish I would have gotten that one. It has a bit of a wider range that it can read. So the residential version only reads 400 to 2,000 parts per million. That's not really it's an okay range. Atmospheric CO2 again is 400 parts per million, and I don't want to go over 2,000, but it'd be nice to see how far over I'm getting if I'm producing too much. So this sensor you can hook up to an Arduino or some kind of microcontroller and read CO2 levels into software, and then in the software you can do a lot of cool stuff with the data that we'll talk about later. That obviously requires some electronic skills, some computer programming skills. That's maybe beyond what a lot of people can do, which is cool. There are other ways you can monitor it, and the one on the right is a fairly cheap solution. I just got one of these a few weeks ago so I could do calibration on my other sensor, and it costs about $61 on Amazon. Not too bad, and it seems pretty accurate from what I can tell. It also gives you the temperature, which is handy as well. So stick that in my greenhouse, and then when I'm in there, I can actually see what's going on, whereas this sensor obviously doesn't have a display. I'd have to go to my computer to visualize exactly the CO2 levels. So I mentioned cool things you can do in software, but you can do cool things just having the data, and we'll go over that. Having it inside the computer means that the computer can do all the work for you and produce automatic data results. But we'll go over the basic math and the cool things that we can do here. And one of them is trying to solve the problem: can we estimate plant growth based on CO2? So here's a chart. The blue line again is the CO2 level, and this is one of the instances where I had the CO2 generator turn on in the morning time as soon as there was at sunrise, basically shoots up to about 2,000 parts per million, and then maintains for some period of time, maybe an hour, and then slowly drops off back down to atmospheric levels over the course of about an hour and 45 minutes. So we know kind of our starting point. We started at 2,000. If we take the upper part of the CO2 level, we know we went from 2,000 down to atmospheric levels, which in my sensor would have read like something around 900 parts per million. So we kind of know how much the plants are consuming. This is it's a somewhat closed environment. There's going to be some leakage with the outside world, but for the most part, the air in there is not circulating too much or mixing too much with the outside world. Very little. The plants are probably consuming the majority of that CO2 over the course of that hour and 45 minutes. So we can probably get an estimate on how much CO2 the plants are using. We can calculate maybe how much growth from that. Now, we're using a propane burner to generate the CO2. So we can do also some cool things with fuel estimation or energy production. And so this table shows the ratios, the specific CO2 emission per kilogram fuel. So in the case of propane, the liquid petroleum gas, for every 1 gram of fuel, it produces 3 grams of CO2. So we'll need that later on in our calculation. So to calculate how much fuel we're using, we need the volume of the greenhouse, and in my situation, my circumstance, it's about 24.5 cubic meters. Then we get the weight, the mass of that air, which is about 30 kilograms. You multiply it by the density, which is 1.22. We take the start CO2 level, which is about 2,000, and then we subtract it from the end to get the difference, the total amount of CO2 consumed. And then we can calculate how much that would weigh in terms of CO2 mass. And it comes out to about 30 grams of CO2. And then we can plug in the ratio of how much fuel how much CO2 is generated per fuel burned, and we come out with about 10 grams of fuel to produce 30 grams of CO2. Now, if we remember our ratio from before, for every 10 grams of CO2, plant can make 6 grams of glucose. So for our 30 grams, our plants grew during that hour and 45 minutes. It grew 21 grams. It produced 21 grams of glucose, which isn't a whole lot, but over the course of a day, if you were to maintain that actually comes out to quite a bit, right? An hour of 45 minutes to produce 21 grams. And then we can obviously calculate, we know how much fuel we're burning. We can calculate how much that costs us per burn, or in this case, we've broken it down to the cost per gram. How much does it cost in terms of burning propane to grow this certain mass of plants? And it comes out to about 2 cents for 21 grams. Every 2 cents you burn may produce about 21 grams of new plant growth. So pretty cool. And we used a 20-gallon tank of protein. It's about 9,000 grams. It cost about $18 to exchange currently at the moment. And we can calculate the cost per gram. It's 0.2 cents per gram to buy. And then from there we can calculate how much plant growth went into that. So in terms of tomatoes, if you were to create a tomato purely from the carbon you burned from propane, that tomato would cost about 43 cents. That's a large tomato. That's about a pound. If you're in the U.S., 454 grams of tomatoes, which at the supermarket can run anywhere from $1.50 to $3, depending on the type. So that's just an interesting little side note there. But I hope that's about all I have. I hope you learned maybe a little bit about CO2 generating, how it can benefit plants, what else you can do with the information that you have based upon CO2 levels, and happy growing from with using your CO2 as efficiently as possible. So with that, please like and subscribe if you like videos like this. And as always, Trip Zero out. We'll see you next time.